DC theory pretty quickly. Particularly the early portion. Yes. Yeah. There they all are. Although they did some weird stuff here, didn't they? They used V, but then used W for power.
Yeah, that's just wrong.
They just put watts instead of
Yes. Yeah. Yeah, but are they metric watts? Or are they... All right, so properties of matter. You guys remember the atom? You know, we still haven't seen one of these guys. We've done a whole lot to make images of them with electron microscope, but with the naked eye, we still haven't seen one of these guys. Okay, we've built a whole lot of really cool stuff though, based on these theories. And pretty much everything in this room, particularly anything that's electronic, works because of these theories. However, what's interesting is pretty regularly we come up with some new derivation or some new modification of these theories. One of the ones that I keep expecting, I'd love to see in my lifetime, but I keep expecting to see is we're going to somebody's suddenly going to understand the relationship of the forces a little bit better, particularly with respect to gravity. And that's going to make some changes. But so the definition is the smallest particle that will retain the properties of that particular matter. Now, truthfully, science has very clearly established that you get into subatomic particles, way small into subatomic particles, the differentiation between what is matter and what is energy begins to disappear. And everything is energy. So that's kind of cool because that sort of means that maybe we could do the transporter thing, right?
Mm-hmm.
Yeah. Or even better, I could say, filet mignon, computer, what did Picard always say? Black tea or Earl Grey. Yeah.
We've been watching too much Star Trek.
Yeah. That'd be cool.
Yeah.
Walk through instead of traffic, just walk through the portal and I'm in Paris for lunch.
Mm-hmm.
Having a croissant. Right? With locks. Yeah, that'd be kind of cool. So
Yeah.
the truth is, though, if we bring a bunch of these atoms together that are the same type of atoms, we're going to call them an element. And all of the atoms will behave the same with respect to each other and with respect to other atoms. Now, how they combine with each other will be very unique to that element. Okay? There are a few elements out there that they don't like to play with anybody. Most other elements, they actually do like combining and interacting and forming into other substances. So if we're going to use the term element, it'll be of single atoms. They can naturally form into compositions of more than one atom. When that occurs, we call that a molecule. So for example, if I take two oxygen atoms and put them together, they'll have a tendency to weakly bond together and form a molecule. And it'll still be an element because they're oxygen. But if I instead take an oxygen molecule and two hydrogen atoms and bring them together, they'll form together too with a pretty significant release of energy and a pretty tight bond, and that will then become what's called a compound. But in both cases, the two oxygens or the oxygen and two hydrogens have formed into a molecule. And a molecule is sort of the basic building block of matter. Okay, compound, more than one type of element. Element, only one type of atom. And there's, I forget, something under 200 different elements out there. My favorite is unobtainium.
Unobtainium?
Sounds
expensive.
funny, but it's true.
Yeah, it's expensive. Unobtainium. All right. typically, anytime these atoms come together or go apart, there'll be either a release of energy or an absorption, consumption of energy, usually in the form of heat. Okay? So like I said, take a bunch of hydrogen atoms and a bunch of oxygen atoms, bring them together, poof, Hindenburg.
Right.
Lots of heat gets released. Okay, and they change from two gases, fairly light gases, into water, release a fair amount of energy. If I want to return them back to being gases, I've got to put the energy back into the system. I take all those water molecules and hit them with a high amount of heat or maybe an electric arc. There's several different ways of doing it. And they will release back into their constituent elements. Okay? This is useful because that means the chemistry between various atoms, we can use that to store energy and then use the energy when we need it. So, all atoms are made up of some particles. There's only 3 particles, although there are occasionally other particles get involved, but semi-particles get involved in the form of different types of emissions or radiation. These 3 building blocks of all atoms, and therefore all matter: protons, neutrons, and electrons. The neutron and the protons are huge. They're like, I forget, 1,800 times bigger than the electron. And as a result, because of the 3 basic forces acting on all of these, they have a tendency to combine or to collect into a center core that we call the nucleus of the atom. The electrons, they have a tendency, because of the force, static force existing between protons and electrons, they have a tendency to hang out in orbit around the atom, and they're moving really fast. They're moving really fast. They're moving really fast, and they're moving in a really small orbit. We said there's like a iota of atoms in a very small amount, right? Okay, so they're really small little orbit, and they're spinning around how fast? At about the speed of light. Okay, 300,000 meters per second. Okay, really, really, really fast. So the end result is, and those orbits aren't perfect. They have a tendency to move around and change as they're spinning around a little bit. It's not that fast in terms of each cycle, but they're moving so fast, it ends up forming a shell. So we tend to use the term shell to describe it. It also turns out that it's really hard to get the protons and neutrons to go other places. And when you do, don't be anywhere near it because it releases a lot of energy. I mean, a whole lot, as in Hiroshima a lot. Okay? Bada bada boom. And so, but the electron on the other hand, the little bitty guy, give it a good slap. In fact, guess what? I can go like this. Okay, I'm moving them, I'm collecting them. Okay, here, come here. Okay? Electrons are real easy. Just a little bit of friction will do that. Right? All right. So then it turns out, because electrons are sort of hermits, they don't like each other. They like protons, but they don't like each other. Protons don't like each other, but the physical force of gravity overcomes the electrostatic force. So they all hang out together. Electrons don't have that problem because they're so tiny, but they still have the same amount of electrostatic force that a proton does. So they don't like each other. So what happens is, if I've got a core and I throw an electron in there, the speed of light, man, it's going pow, pow, pow. It's going so fast, it's centrifugal force and all the stuff that's going on, it sort of sits there. But it's in pretty tight. If I throw another electron in there, that other electron's going to go, and they're going to avoid each other. They're going to stay exactly opposite of each other. And they're going to be in such a tight shell that if I throw a third one in there, they're all going to go, this isn't going to work, you can't be here, form your own dang shell. So they're going to make it sit in the next shell out. Well, now that's a bigger diameter. So that outer shell can now hold quite a bit more number of electrons until it gets full. And then they say, yeah, get out of here, no more. So a third shell forms, and then a fourth, depending on how many you've got. So it's a little odd. What'll happen is 2 in the inner shell, max, period. Then 8 in the next shell. Then 8 in the next shell. However, once that shell, the next shell starts getting full, what'll happen is it'll allow the third shell to start taking on some more. So there's a little bit of a difference in that third and fourth shell. And of course, you can only have so many shells because we run out of, we don't know, there's only, like I say, 150 or 160 different elements. So 99.9% of everything we deal with is going to be, you know, in the first few shells. That's going to constitute most of matter. When you start getting out to the fourth shell and the fifth shell, it's really only the very odd, bizarre, very unstable elements. So it turns out that the outer shell really matters. If the outer shell is full, I mean, that's the recipe for a hermit. If the outer shell is full, it says, I don't have to play with anybody. And it won't. It will not bond with any other molecule, its own type or any other one. So it turns out there's 5 or 6 elements that are that way, where the outer shell is perfectly full. We call them the noble gases. Okay, argon, neon, helium. Helium, it's got 2 electrons. Outer shell is full. Okay? Because the outer shell is full, it will not chemically, electrically, or otherwise interact with anyone else. It actually can be inspired to electrically interact, but argon is another one where, man, that outer shell is chock full, so it doesn't want to play. It doesn't like forming into solids, doesn't like forming into liquids. It can, you can get anything cold enough to solidify it, but however, these the ones that have either a shell that's almost completely full, it's missing 1 electron, or they've only got 1 electron in the outer shell, like copper and silver. Okay? Yeah, we don't need that stinking electron. You want to borrow it? It's all yours. Sure, go ahead. A lot of plastics, by the way, are that way too. It turns out that there's a few elements, carbon, silicon, a few others, where the shell is half full. This is pretty cool. We haven't known about this for too long. It's really only been about the last 50 years. Turns out these guys, you can fake them into taking electrons or giving up electrons, depending on what you do. You can turn them on or turn them off. Okay, so you can change how they behave based upon how we construct and build the material. Okay. So the end result is you're going to end up with material that likes to conduct, sort of likes to conduct, doesn't like to conduct. But that's a long word, so we'll make up the word insulating instead of doesn't like to conduct. Okay. Now, having said that, just because it doesn't like to conduct doesn't mean it won't conduct. Okay, if you get enough coulombs on one side, creating enough voltage potential, anything will conduct. I know human beings will conduct because I've conducted a lot of electricity over the years. It goes right through you, boom. You guys ever play the game when you were a kid? You probably didn't know what a lawnmower was. They still have lawnmowers.
Hold on to the mag.
You get all the kids in the neighborhood, right? You pull the secondary coil off the spark plug, right? One kid would grab the end of the spark plug lead, and they all hold hands all around in a big circle. The other kid would grab the case of the engine, and somebody would sit there and start pulling on it. The whole circle's getting zapped. Of course, the first one to freak out and let go is the chicken, right? Yeah, it was pretty stupid because we're driving that current right across our heart. All right, we didn't know if any one of us might have a little myocardial infarction going on or something. Um, Okay, semiconductors sort of Conductor loves to conduct electricity, an insulator. Now the other side of this is, particularly with a conductor, but even true with semiconductor, organic materials, silicon, some other ones. The electrons in here are sort of bouncing around. They're moving, they're trading, they're doing strange stuff. In a conductor, they're wandering all over the place. Anytime any static or magnetic field is felt, which is happening from the planet, there's electrons traveling all the way around, all over the place. It's a sort of a disassociated array of electron movement. That doesn't mean anything to us. So when we talk about electron movement or electricity, we're talking about a coordinated effort of the electrons moving in a single direction, going in a single direction in the conductor. Okay? And even within that, there may be some electrons traveling in a sort of disassociated, unorganized manner. So we might actually change the shape of a conductor to help reduce that. So yeah, the atoms of the full valence shell, that outer shell, valence shell is the shell that likes to chemically interact. That's the outer shell. If the shells down below start chemically interacting, you're pretty close to fission or fusion. It's going to not be too much longer before you start getting a nuclear reaction. And we use nuclear because we're talking about the nucleus of the atom starts reacting. And that releases just a boatload of energy. All right, so yeah, so when they combine or when they do various things, they share electrons. I think I say it later, so I won't go there yet. It is true that if I take one element that's a really good conductor and another element that's a really good conductor and bring them together and make a compound, they may not be as good a conductor. Or they may be a better conductor. Or maybe they become a good insulator. That's also true with respect to some of the other forces. With respect to electricity, we've really been talking about the electrostatic force. What happens when I take just a small amount of nickel and add it to iron in terms of being able to condense and reflect magnetic lines of flux? So it's a small amount of nickel and add it to iron. A little bit of carbon, a little bit of nickel. Almost completely eliminates the ability of that steel to hold and retain magnetic properties, called stainless steel. And just a small amount of nickel radically affect its magnetic properties. So, and there's no universal rule there. It's just some stuff, others not. Okay, same thing. Hydrocarbon compounds, by the way, which includes us, wood, trees, the dog, the cat. All of the hydrocarbon compounds are pretty good conductors, and they're really good conductors when you fill them full of water, which we are full of water. Okay? All those little hydrocarbon cell, wrapped cells that we have that our body's made of, they're all filled with water. And water is a pretty good conductor, as conductors go. This picture shows the various the inert gases or noble gases. It's helium, neon, argon, krypton, xenon, something, I don't know. So the problem with a good insulator, this is a great insulator, except you can't get it to stay anywhere. Okay, I'm going to wrap you, argon, I'm going to wrap you around this wire, and you stay there. Don't go anywhere. Get the gas, right? They're gone. It doesn't like combining into a solid at all. It'd make a great insulator if I could get it to solidify, but it won't solidify. So we're going to have to come up with some combination or qualities of characteristics of elements to produce a compound that's a pretty good insulator. However, there are also going to be some other things depending on the environmental constraints of where this conductor and insulator exists. So if it's in a hot environment, if it's in an area where mechanical behavior occurs a lot, we're gonna have to do some different things. So then as we get into these particular subatomic particles, we have to talk about the forces that exist between them. So I've already mentioned a little bit of, I've mentioned the term electrostatic force. Electrostatic force is a force of repulsion or attraction that exists between protons and protons, electrons and electrons, and electrons and protons. Another dominant force that can exist between protons and electrons, or that and actually can emanate from protons and electrons, more so electrons, is a magnetic force. And it'll have characteristics of behavior that are very specific to the orientation of the static force. The third force, and the magnetic force is also repulsion or attraction, so there's a directionality to it, right? The third force is gravitational force, and that's actually a very powerful force. It's not as powerful as these two in small quantities, but it's a pretty powerful force, and it's only unidirectional. Gravitational only attracts. There's never a repulsion with gravitation. Now my guess is at some point we will figure out, we have figured out how to manipulate the relationship between static and magnetic force. We can use static force to create magnetic force, and we can use magnetic force to create static force. We've known that for a long, long time. What we haven't figured out is how to use one or both of these to affect gravitational force. We'll eventually figure that one out, which would be kind of cool. So it turns out neutrons, they don't really have magnetic or static force, but they do have gravitational force. So, so they do create attraction, and thus the large mass of the neutron and the proton, the gravitational force is enough to keep them all pulled together, right? It overcomes the static force that exists between the protons trying to push themselves apart because they're so big. The electrons being 18 or 1900 times smaller, there isn't enough mass to have a very strong gravitational force, but they still have the exact same amount of electrostatic force that the much bigger proton does. So if a proton has 1 unit of force of attraction, the electron has 1 unit of attraction as well. Even though it's physically much, much smaller. So because there's sort of this attraction and repulsion thing going on with electrostatic force and electromagnetic force, if direction matters, which it often does to us, then polarizing is also going to matter. And we're going to have to come up with vernacular or terms to define the polarization. Right? Now, to me, it would have been logical to use the same kind of terms. Well, but the truth is, we sort of figured out magnetic force long before, and were able to make use of it long before we were able to make use of electrostatic force. We knew what it was, and every once in a while we got zapped by it because the sky would come together, and sky gods would come together and burn a hole in the top of our head, the lightning bolt. But for the most part, we really didn't understand that so well. However, we did figure out that the Earth is a big magnet. If we take and make a small magnet and suspend it in a way that it can spin around, it would orient itself to the Earth. And the chartographers came up, the map makers came up with, you know, the poles, the North Pole, which is my pole, by the way, and the South Pole, and then came up with these terms. Well, along came the scientists that developed electricity, and they went with the mathematical operators, plus and minus, so it's a little confusing. Anything can be, as I said, have electrons move through it, jump across it, be, you know, electrocuted, etc. As well, anything, if it's matter, can be magnetized. Anything can be magnetized. However, very, very few elements will retain that magnetism for any length of time. When I say any length of time, milliseconds or microseconds. It'll be magnetized and then it'll go back to being random magnetization. When we talk about magnetism, that'll make more sense. All right, so the polarization between electrons and protons exists. It's one of attraction. And we use, because polarization matters, we use arrows to define directionality. Now, in the case of electrostatic polarization, the arrows don't mean that much unless we get into antenna communication, where we're using an electromagnetic, which is electrostatic and magnetic pulse to create a signal. Then the directionality of the arrows matters a little bit, because we can use it to sort of shape the signals. But for the most part, we don't use that too much. In the realm of magnetism, we do the same thing, and their directionality really matters because it determines which way something's going to move, if we're going to use magnetism to move things. So, in general, for both of them, likes repel, opposites attract. So if there's a plus and a minus, they like each other. If there's a minus and a minus, they don't like each other. If there's a plus and a plus, they don't like each other. However, we don't have to worry about the plus and the plus because they're going to be in the nucleus and they're never going to come out to play, hopefully. If they do, we're not going to be here for long. And then you may see a question out there. Technically, they do orient from positive to negative. Okay, so if arrows are used in defining electrostatic lines of force, the arrows point from positive to negative. Why is that convention? Well, because as we were playing around with this way back when, we didn't actually know that electrons go the other direction. We thought they went from positive to negative in a chemical power supply. It turns out they actually don't. They go from negative to positive. So we're completely backwards on everything. And until we got into semiconductor technology, where that mattered, we didn't know it. We didn't realize it.
Is that because the outer shell, the valence has more negative charge that it wants to go release to the positive? This is the old theory, but the new theory, is it because the negative charge has a abundance of negative?
No.
Is that the right way of looking at it?
We just made a choice without knowing any better,
Right.
And created chemical interaction, which we call a battery.
Right.
And we presumed electrons go from positive to negative.
And it's just the opposite.
And it's just the opposite. The truth is, other than in battery use and solid state technology, we don't care. It's not relevant.
Good.
Because they go both ways.
Right.
But you're asking why, though, right?
What's that?
You're asking why it's happening?
Yeah, why is it happening?
Yeah.
I'm asking why it's happening. Is it because I thought there was an abundance of negative charges on the valence shell or something.
Well, but that's true throughout the entire. So I'm sitting in a big field of copper. That's true for
Right.
all of them.
Right.
Right.
Okay.
If I take that conductor and connect it to a galvanic relationship, which is a battery,
Right.
electrons are going to go one way or the other.
Mhm.
We picked minus for one lead and plus for the other, and sort of went down that rabbit hole.
Okay.
And then it wasn't until we got into semiconductors where we could define you get to go this way, but you don't get to go that way. So the basic semiconductor unit, the diode, allowed us to have directionality, and only it allowed conduction in the direction opposite of what we thought was going on. And then we went,
But you're asking why the reaction, right?
Mhm.
You're explaining what the idea came from. He's asking why does it
well,
happen?
I haven't gotten into batteries
Okay.
yet.
Okay.
That's-
We're gonna get there.
Yeah, well, we will get to yeah.
Got it.
And the short answer is it's a chemical reaction. Electrons always move in a chemical reaction.
Yeah.
So if I bring an oxygen molecule and two hydrogen molecules together, what's gonna happen is the electrons going around the hydrogen atoms are going to, first off, there's gonna be a release of energy as they come together. And then the oxygen molecule is basically gonna rob the two electrons. So the hydrogen atoms will sit there being very positive. And the orbits of the electrons, of all now 10 electrons, are gonna be pretty well around the oxygen atom. So now the oxygen atom is gonna be kind of negative, and the hydrogen atoms will be somewhat positive. And so when I get a bunch of those compounds together, they'll tend to line up. And they actually will do a lot of really weird stuff. Water is actually one of the more weird elements out there. One of the few that will expand when it goes from liquid to solid. And again, it's because of that weird behavior. But that, in the moment that they come together, electricity is happening. A very small amount is happening. And then the rest of it, in terms of directionality, it's directionality is just going to be a function of who's got the higher charge. Okay, if you're sitting still and I come along and friction wipe a bunch of electrons off, okay, I've got a bunch of electrons. I'm now much more negatively charged than you are. I can hand them to you, and they're going to go from me to you.
Right.
And we didn't sort of get the sense that that was happening. That's what was happening. And in fact, it was probably a function of the human's inability to sense. It looked an awful lot like the lightning bolt was coming from the cloud down. But now that we've got really, really high speed photography and the ability to tell it, almost always lightning starts from the ground and goes up. The ion field builds downwards, and the electron travel goes up, and it usually overcharges, and then it comes back down. Okay. All right, so magnetic polarity turns out much like the electrostatic force, it can be depicted in lines of force or concentrations, linear concentrations. And in fact, if we take a bunch of small, little bitty ground up pieces of magnetic material, iron filings in this case, and lay them out, they not only will they model sort of the shape of the field, but they'll actually concentrate in and around these individual lines and form the individual lines of force. This picture clearly illustrates that the force isn't this uniform field. It's sort of concentrated lines going from one direction to another. Now, do we care if the lines of force go from here to here or from here to here? The iron filings obviously don't care. But we had to come up with some vernacular, because if we're going to use this to move things, we got to show some arrows, and you'll see that eventually, particularly when you get into mirror. We've got to come up with some arrows that show some directionality, because what's going to happen is these lines of force, if I take another magnet and similar lines of force, if the directionality isn't considered, they'll either all combine or they'll all push each other away. So directionality matters. We label them north and then south, and we label them such that the magnetic lines of flux emanate from me, north. Okay? All things magnetic emanate
That's the
from
center
me.
of the universe. Right?
Yeah, exactly. They emanate from me, north to the south.
Okay.
Okay? It's easy for me to remember. You guys got to figure something else out. Kind of like when you're standing on the North Pole, which way is south? Yes.
Yeah.
Okay. Up isn't. So we came up with some vernacular. We just said, okay, arrows going in a direction. Okay? And that way, when we bring the two magnets together, if the arrows are lining up, they're not going to like each other. If the arrows aren't lining up, they're going to like each other.
Right.
Okay. Here's another example of a bunch of little magnetized arrows, right? It doesn't quite show the lines that well, but you can sort of see all the arrows pointing in, and they sort of wrap around, and then they're pointing out here. Okay? Somebody had to go out and buy or build a whole bunch of little compasses to take that picture. So it turns out that there's a really cool behavior between the electron or electrostatic force and magnetic force. If we take a bunch of electrons and get them to move in an organized manner, and actually it does occur even when they're unorganized, the problem is it's not useful to us because all the disorganized movement creates disorganized magnetic fields, which all counter-cancel each other. And we call that eddy current, or eddy magnetism if you're looking at the other direction. But if we can get all the electrons to sort of go in lockstep and conduct down a path, they will cause magnetic lines of flux to form. The magnetic lines of flux will form at right angles to the direction of travel. So the magnetic lines of flux will form around in a circle around the direction of travel, emanating outwards. The more electron travel, the more magnetic lines of flux occur. Similarly, if I have a magnetic lines of flux, maybe I got a big magnet here with two poles there, and I take a conductor and start moving it through those magnetic lines of flux, that movement will cause, if it's at right angles to the magnetic lines of flux, will cause the electrons to move. Okay, that's huge for us. That means we can take physical motion and make electricity, or we can take electricity and make physical motion. Really, really change life as we know it. Okay, a mere 150 years ago, we couldn't do this. Okay, even a mere 100 years ago, we weren't that good at doing it. We could do it, but we weren't that good at it. All right? That completely changed. Have you guys ever tried to live without water, live without light, live without all the other advantages? Okay, the reason the water comes out the little tap in the end is because of electricity. Because we can take magnetism and move electrons, and because we can take electrons and make magnetism. Okay, this was really, really, really huge. It also turns out that, so just for the vernacular, I've used it. The magnetic lines of force are known as flux, and there are a whole bunch of parameters for measuring it. The amount of flux lines per area, flux density. There's a whole bunch of other terms which I may touch on here in a few slides, but most of that I don't know that we're not going to be doing too much engineering with any of that. So, but this important relationship is really, really critical to us. The other thing that's important to us is there are a few materials out there that if you influence them with magnetic lines of flux, they will stay magnetized. Okay, iron is the big one. And in fact, something very, very unique to this planet, not true in most other planets, is that it's about 98% of it is made out of iron. And it's very highly magnetized. It's a very unusual situation. But, you know, out till, I forget what it is. Well, from volcanoes, it's at the surface. But the bulk of the planet's a pretty thin crust, a few hundred miles thick. And everything inside of that is iron. Okay? And it's all pretty well magnetized. So, and it holds its magnetism.
How long does it hold on magnetism for?
For the purposes of everything we're doing, it's indefinite. But magnetism does decay. The reason the planet doesn't decay is because it's constantly being remagnetized by the energy coming off of the sun, the electromagnetic radiation coming off the sun. Okay? So when the sun burns out, a few years after that, your compass is going to stop working. Sorry.
I get lost there.
That's okay. When the sun burns out, we're going to be incinerated anyways. So your compass is going to be kind of a moot point.
The iron core, is that why we have a north and a south pole?
Yes.
Okay.
It's a big magnet. It's a circular one, but it's a big magnet.
And why do they change polarities?
We haven't worked that one out. It needs to happen, I think, before.
Okay.
They think it's a big radiation burst from the sun. That's about the only thing that would make sense. And somehow, just like you use AC to degauss something, somehow the sun does that.
Have they figured out how gravity works into it?
That's the thing would be pretty cool to sort out. Think that you could take and make your car weigh 4 pounds instead of 4,000 pounds. A
Well,
couple of little stubby wings and you're flying around. Yeah, baby.
well, that's what I was watching a video on super cooling or whatever it was that where they can really take a lot of weight and with the super cooling. Have you seen that?
I've seen several things. Supercooling is leading us to better understanding gravity.
And that
It's also leading us to better understanding conductivity.
it's also helped. I've noticed that they can hover like over the coils like something very heavy that normally you can't lift.
Right, yeah, we know it affects gravity.
That's interesting.
We're not there yet. But they've also, I think there were a couple of a group of scientists in Sweden somewhere have clearly 100% irrefutably demonstrated the act of taking several atomic particles and relocating them in a different spot. Just from here, they ceased to exist and they started existing here.
So it's just a matter of time.
Is that what they did with the big collider?
Literally.
Yeah, it's something to do with the big collider. They've managed to make that happen.
That's pretty interesting.
It's pretty amazing stuff.
Yeah.
Okay,
Super cool.
it's also important to note there's no common rule between what makes a good electron conductor versus a good flux conductor. So those lines of force that I showed you, if I get iron near them, they'll all stop being nice and round. They'll all jump into that iron. It's a good conductor. Just like the lightning bolt, if I put a lightning rod there, man, it's going over the lightning rod because it's a good electrostatic conductor. Just because it's a good electron conductor doesn't mean it's a good flux conductor. So for example, stainless steel, it'll conduct electricity just fine, right? But it does not like conducting magnetic lines of force. So we use the term permeability to describe something that loves to conduct magnetic lines of flux, and instead of conductor, and we use a reluctance to describe behavior that doesn't like to conduct lines of flux. So like a conductor is to an insulator, permeability is to reluctance for magnetism, right? Okay, and that's also true with insulators. A good electron insulator, how about Teflon? Teflon's a great electron insulator. Okay, magnetic lines of flux will pass right through it. In fact, there's a derivation of Teflon called Kaptron by the brand name, that if you subject it to enough magnetic lines of flux and a little bit of heat, it'll turn into a primer cord fuse and ignite with a whole lot of force. There's a whole bunch of airplanes sitting out in the desert that they used this to build them with and then figured out, oops, we shouldn't have used this stuff as an insulation. It ain't good. So there's no hard and fast rule between conductors, insulators, permeability, and reluctance.
So reluctance is just opposite of permeable.
Right, just like insulator is the opposite of conductor. It's important to note that all of these forces weaken very, very quickly, exponentially with distance. So my weight, okay, it's a Sevelt 120 pounds. Right? I go up 100 feet, it's going to be 119 something. Right, I go up 200 feet, it's going to be 117. Okay, I go up 400 feet, it's going to be 112. It's going to start decaying pretty quickly. I don't know that distance is exactly correct, but I don't have to go too far away before the gravitational effect. By the way, I'm not pulling that hard against the Earth, but the Earth is pulling very hard against me. The effect of Earth's gravity is going to decay very, very quickly with distance. The same thing is true with two electrons. They don't like each other, and the more I push them together, the more they push apart. But I don't have to get very far apart, okay? Like one iota apart, right? Or what is it, yocto, one yocto apart, right? Before, the forces don't mean anything. So proximity is going to matter. Same thing is true with a magnet. You take the north pole of a magnet, nothing, no problem. A little bit of work. You don't know what you do. Right in there, they are not coming together. Okay, that force suddenly gets really, really strong. Out here, no big deal. So that proximity is not linear, but it's pretty significant when you get pretty close. Therefore, if we're going to try and make a magnet cause electrons to move, or electron movement to cause something to physically move, we want them to stay fairly close to each other. We're going to design all this stuff to be pretty tightly packaged. The last thing out there is that's a form of energy, is called electromagnetic radiation, and one spectrum of electromagnetic radiation, we call it light. But in every instance, electromagnetic radiation, we treat it as if it's an energy packet. The packets act like particles. They behave like particles. So for example, particles leave the sun and come out here, 6 minutes later. Okay? If they can sneak around the moon in time, we call those photons. They truly are energy, but there's a relationship between some of these. If I can get, for example, if I can get material, any matter, to warm up and get quite hot, it'll get so excited, so thermally activated that photons will start, these energy packets will start coming off of it. That's what happens to the filament of an incandescent bulb. It's so thermally activated that it starts throwing off these photon packets. Well, it turns out any conductor throws off packets of energy if electrons are traveling through it in the form of electromagnetic radiation. Any conductor will send out a radio signal. Okay, usually it's garbage, it's not intelligent, and the higher the voltage, the further it'll emanate, but even low voltage will send out some form of electromagnetic radiation. Well, it turns out if those packets are behaving in a very narrow frequency of radiation, our little orbs back here can sense them, and can actually see. They physically react, and now we can see each other because of this. All right. And it turns out that these little packets bounce off of stuff. It's kind of useful. And they change behavior as they bounce off of stuff, which gives us a whole bunch of different colors. The other thing about matter, I think we'll start with my break. Yeah, this is going to be a good place. So, all matter is subjected, or can potentially change temperature. Now, it's important to note that temperature is not heat energy. They're two different things. Heat energy is a quantity of energy that's available, like the quantity of light packets. Okay. Temperature is a measure of the state of molecular excitation. So if I take it all the way down to minus 273 degrees Celsius, or minus whatever it is, 500 and whatever it is, 59 degrees Fahrenheit, all molecular activity will stop. All the molecules will stop bouncing. They'll get denser and denser and stop bouncing. Of course, as they get more and more compressed, they become better conductors. This property is actually so profound, you could take a piece of metal with a little dent in it and super cool it to the point that it'll shrink that dent back out of it. Let it warm back up and the dent will be gone. Okay? So it turns out that if we change the temperature of any matter, its ability to conduct electricity will change. Now this is where it gets really weird. For some matter, as you heat it up, its conductivity goes down. Its ability to conduct goes down. It gets more resistance. For other matter, as you heat it up, its conductivity goes up. And for all matter, there'll be sort of some threshold where this reverses. Okay, so part of what happens in a light bulb is when you go first turn the electricity on, that little piece of tungsten wire has very, very low resistance. As it starts to heat up, its resistance starts going up. It gets to the point where it is bright hot. I mean, it's emitting photons in every direction, and its resistance goes way, way, way up. Okay, so that's a sort of a positive coefficient. As it gets hotter, its resistance goes up. Carbon, on the other hand, is the other way. It's a negative coefficient. As it gets hotter up to a point, its resistance goes down. Okay, so again, we need to just know about this, and then of course, from the engineering perspective, once we know about it, we map it out, we plot it out, and we can use things like a little piece of carbon to measure temperature, or a little piece of tungsten to make light. Okay. And then we can chart it all out and plot it all out. All right, so I ran a little over. So how about we come back at a quarter till, and then we'll continue through, not too much more properties of matter. Start talking